Introduction to Orthogonal Frequency Division Multiplexing, aka OFDM, a surface view of what, how, and why. Created, prepared, researched, and presented by moi, Sheldon Hunter. What to expect? I'm hoping to provide more information than you previously knew about OFDM. We're going to learn some terms. We will discuss what is OFDM, the purpose of OFDM, OFDM versus previous generation technologies. Before OFDM, several technologies were used in wireless and communication systems, including single carrier modulation that transmitted data on a single carrier frequency, frequency division multiplexing, or FDM, which allowed multiple signals to be transmitted simultaneously by assigning different frequencies, but without the orthogonal properties of OFDM. Time division multiplexing, or TDM, where time slots were used for different signals, but it wasn't as efficient in multipath environments as OFDM. We will look at the various fields and technologies where OFDM is utilized, how OFDM works, advantages and disadvantages. Then we will conclude. Terms to know. Orthogonal in regards to OFDM is when subcarriers don't interfere with each other even though they are closely spaced. Subcarrier, a subdivided channel that carries parts of traffic. Multiplex, the term comes from the word multiple and plex. Plex meaning layers or parts, thus giving multiple parts or multiple layers. Spectral efficiency is efficient use of bandwidth. Multipath is when a signal like a radio or Wi-Fi signal bounces off different things like walls or buildings and takes different paths to reach its destination. Modulation in regards to OFDM is the process of transforming digital bits into radio waves over specific subcarrier frequencies. Here is an example of multipath where the transmitter sends a signal to the receiver and it bounces off the building before it reaches the receiver, showing why it can be difficult to troubleshoot radio wave communication. What is OFDM? Orthogonal frequency division multiplexing is a digital modulation technique that splits a signal into multiple smaller subsignals transmitted simultaneously at different frequencies. Think of OFDM like delivering a big stack of pizzas to different houses. Instead of one driver taking all the pizzas in one trip, risking some getting cold or lost, you send many delivery drivers, each carrying just a few pizzas to different locations. This way, even if one driver gets stuck in traffic, the rest of the pizzas still get delivered safely and warm. OFDM is just like that. Instead of sending all the data at once on one frequency, which could get stuck with interference, it sends smaller bits of data on different frequencies to make sure it all arrives safely. In a single carrier modulation, you see the traffic has nowhere to go if interference is present. But if we break that traffic up into small subcarriers, we see that when some traffic receives interference, most of the traffic still gets through. And looking at figure 1 in OFDM, when one wave is at its peak, the others are crossing zero. This is the zero line, this black one coming across here. This alignment prevents the waves from interfering with each other even though they share the same frequency band. In traditional frequency division multiplexing, on the other hand, looking at figure 2 in the middle, subcarriers are spaced farther apart to avoid interference, leading to less efficient use of the bandwidth. In frequency division multiplexing, FDM, guard bands are used. There are small frequency gaps placed between adjacent channels to prevent overlap and interference. They act like buffers ensuring that signals from one channel don't spill into another, which could cause distortion or noise. The guard bands help improve signal clarity. They also waste some bandwidth, though, making FDM less bandwidth efficient compared to more modern techniques like OFDM, which eliminates the need for guard bands through orthogonal subcarriers. And looking at figure 4, the bottom arrow represents a link of bandwidth at a gigabit per second. Just above that is a representation of FDM showing non-overlapping adjacent subchannels carrying 20 megabits per second of data each. You multiply that by 5 subcarriers and your throughput is 100 megabits per second on this 1 gigabit link. The line above that one represents OFDM. Using the same 1 gigabit per second bandwidth, you see that the OFDM modulation technique increases throughput by making better usage of the bandwidth. That imagery shows at least double the throughput, but could be more throughput depending. The diagram shows channels 1, 6, and 11 on the 2.4 gigahertz band. Each 20 megahertz channel has 64 subcarriers. 52 of the subcarriers are used for data. For those of us that like to think people weren't as smart back in the day, etc., OFDM was conceptualized in 1966 by Robert W. Chang. The purpose of OFDM: efficient transmission over wireless channels with minimal interference. It reduces multipath fading and intersymbol interference, handles high data rates effectively. OFDM versus previous gen technology. Modulation techniques are listed along the top row and the features are on the left. You can see based on the side-by-side comparison of the modulation techniques that non-OFDM techniques are more susceptible to interference due to multipath and have lesser efficient use of the bandwidth. And as a refresher, multipath occurs when a signal takes multiple paths to reach the receiver due to reflections on building, trees, other objects, causing interference or signal distortion. Resilience to multipath, on the other hand, interference means that the communication system is designed to handle or mitigate these distortions and interference. Technologies like OFDM, as mentioned earlier, are particularly good at providing resilience to multipath. By dividing data into smaller streams sent over multiple subcarriers, OFDM ensures that even if some of the subcarriers are affected by multipath interference, the overall data transmission remains reliable. This is especially important in modern communications systems like Wi-Fi, LTE, 5G, which operate in complex environments where multipath effects are unavoidable. FDM and time division multiplexing use multiple signals as well, but TDM will still have issues with multipath because you're just setting a time to send signals and not accounting for the interference of multipath. This causes signals sent at a particular time to overlap and interfere with more recent data that's sent. FDM is just not as efficient as OFDM and not as resilient to multipath. Applications of OFDM. Wi-Fi 802.11 standards use OFDM and cellular uses OFDM as well. How OFDM works. So step 1, input data is split into several parallel streams. Step 2, each stream converts data to waves. Step 3, subcarriers are orthogonal, minimizing interference. And step 4, signals are transmitted simultaneously. Each subcarrier can be modulated or converted from bits to waves with data independently from the others, making the system flexible and resilient to interference or signal fading on specific frequencies. Here's another good analogy for this. So think of a 5-lane highway and all the traffic having to traverse the middle lane, and there happens to be a traffic jam. There would be nowhere for the traffic to go and would be delayed. So think of that as single carrier modulation technique. On the other hand, Imagine having 5 lanes open and using all 5. Then when the middle lane is blocked, most of the traffic still has avenues to continue to its destination. With the added error correction code named forward error correction, or FEC, that recovers data, now you enhance the reliability of the data reaching its destination. FEC would like, FEC would be like a fast tow truck clearing the path on the middle lane of that highway. If that if that tow truck fails, then the system may initiate a retransmission. So this animation depicts multiple orthogonal subcarriers simultaneously traveling and one subcarrier being blocked. Once that middle subcarrier is blocked, the FEC, or forward error correction code, swoops in with a hint for the missing data. Soon after, the receiving host will be able to decipher the message traffic. The error checking by FEC is done at layer 4, and the subcarriers operate on layer 1. Forward error correction is like sending a letter to your friend, but parts of the letter get messed up or torn off on the way. So in order to make sure your friend can still read it, you decide to write challenge questions or draw pictures of what you're talking about. So even if some words are missing or illegible, your friends can guess what was there because of the extra clues that you added. You ask how errors are detected. The receiver checks the message against those extra clues. If something doesn't match, it knows an error happened and tries to fix it using those clues. So in layman terms, FEC adds backup information to fix mistakes. Advantages of OFDM. OFDM supports higher data rates compared to FDM for several reasons. Efficient bandwidth usage. In OFDM, subcarriers are closely spaced but orthogonal, meaning they don't interfere, allowing more data to be packed into the same bandwidth. Resilience to interference. OFDM handles multipath interference better, reducing errors and increasing efficiency, especially in high-speed wireless environments. You ask how? So imagine you throw a ball at a wall and it bounces back to you. But if there are many walls, the ball might bounce off different walls and reach you at different times. That's like multipath in wireless signals. OFDM is like having many tiny balls instead of one big ball. So even if some balls, which represent signals, bounce around and take longer, most of them get through cleanly. Since they're spread out, the system can fix any that get messed up, making it better at handling these delays than older systems. This first animation, you see the ball comes right back when there is only one big ball and one wall, simulating minimal interference. The second animation, you see the ball takes longer to come back, and the time it takes to come back will vary due to more multipath interference. So the third animation depicts multiple smaller balls bouncing off multiple walls. While some may take longer than others, any that get messed up can be fixed. The smaller balls represent subcarriers and the walls represent multipath. You see, traffic still gets through faster, even though it may not um, be all of it, but the FEC can account for the missing data. Disadvantages of OFDM. The complexity of OFDM is a disadvantage because it means that devices using OFDM need more powerful hardware, increased power consumption, more precise timing, and that can be more expensive, harder to implement, less efficient in low power devices like older or simpler systems. Also, any small misalignment in frequency can affect performance. In conclusion, OFDM is a foundational technology in modern wireless communication. It is vital in the evolution of 5G and beyond. Here are some references that I use that you guys might want to go back and read or